Hello friends, we're going to be learning about real numbers today. This is lesson 5 in our course, and we're going to do a whole lot in this. We're going to be simplifying square roots of perfect squares. So for example, we can simplify square root 16 to be positive 4. We're going to approximate square roots of non-perfect squares. So for example, square root of 17, we're going to see is a little bit bigger than square root 16, but we're not going to know exactly what it is, so we're going to approximate it. We're going to identify rational and irrational numbers. These are going to make up the entire real number system. Okay, so we're going to be able to divide all real numbers, which notice is the title of the lesson, into two groups, rational and irrational. And essentially, we're going to be splitting them into these first two groups, where square root 17, because we have to approximate, that's going to be an irrational one, and square root 16, because we know exactly what it is, that's going to be a rational number. Then we're going to use a couple different properties. So the commutative and associative properties allow us to rearrange and regroup things. The identity and inverse properties are going to allow us mostly to solve equations. And then properties of 0, that one's a really easy one. We're just going to say that 0 on top means the fraction equals 0. 0 on bottom means we don't know what it is, so we'll call it undefined. And finally, the arguably most important thing in this lesson is going to be the distributive property, which we will use over and over and over again in this class. All right, so the application we are building up to. You are at Secrets Playa in Cancun. Ooh, lucky you. This is an all-inclusive resort. And you have brought with you $250 of cash to use for tipping. That way, every time you get a service, even though the item might be free, you still want to tip the staff there. And so your plan is to tip $4 every time that you go and get a drink of water, of course. And so we want to find out what is the largest number of drinks of water that you can have before you run out of your tipping cash. And what we're going to see later in this lesson is that although we already learned how to do division in this class, so we can just do the division right now, we're going to learn that context in real life will often cause us to round in one direction or the other. So when we get there and we come back to this one, we're going to see we will have to round this answer because it's not a whole number. And we're going to have a very good reason as to why we round in the direction that we do. All right, so getting started, let's talk about irrational and rational numbers. We have two groups. Okay, if I can just draw a little circle for you here. Inside of this, I said circle, but this is an oval. So inside of this oval, we're going to have two groups of numbers. So I'm going to split this in half. The entire red circle or red oval here is going to represent all real numbers. But inside of that group, we're going to have two different types of numbers. We're going to have rational numbers on the left, and we will denote these with a fancy Q. All right? And then we're going to have irrational numbers on the right, and we can denote these with a very similar fancy Q, but we're going to put a prime on it. Okay, prime is just an apostrophe, for those that don't know, like an apostrophe S when you're writing English words. Okay, so as you can see, the entire set of real numbers, that entire red oval, is completely taken up by these two groups. And so what I'm going to do right now is I'm going to define what a rational number is for you, but then the definition of an irrational number is just going to be the exact opposite definition, because anything that is not rational is going to have to be irrational. That way we make up this entire set of real numbers. Okay, so a rational number is a number of the form p over q, where both p and q are integers. So for example, we know what integers are. Those are positive and negative whole numbers. So rational numbers are essentially just fractions, where top and bottom of the fraction, numerator and denominator, are positive or negative whole numbers. So negative 1 over 3, negative 1 and 3, both integers, so this is a rational number. Positive 7 over 9, integer over integer, that's a rational number. And then something that might not seem like it fits this description, if I have positive 2, or any whole number, this is the same thing as positive 2 over 1, and so I can rewrite any whole number as a fraction, and then I can make it fit that definition of a rational number. All right, and then if we see these numbers as decimals, these decimals are not going to terminate, they are going to terminate or they're going to repeat. So anything that can be written as an integer over an integer will either terminate or repeat, Where terminate just means that it stops. So like 0.1, it doesn't go on, it just stops, okay? That is going to be a terminating decimal. And repeating might be like 0.333, where those threes repeat, okay? And whenever you have repetition like that, that is also going to mean that it can be written as a fraction. So for these two examples, I'm going to show you that 0.1 is the same thing as 1 over 10. And 0.33333, we can rewrite this in two ways. One way is to put a bar over the threes to represent that repetition happens. And the other way is as a fraction, which is what we really want right now. This is 1 over 3, 1/3. Okay, and I need to make one note here. When I wrote 0.333, really these threes keep going, so I should actually put a little dot, dot, dot. Okay, everyone see this little dot, dot, dot right here at the end? Because if those dots aren't there, then it actually is a terminating decimal. So we need the dot, dot, dot in order to represent that those threes keep on going. All right, so a rational number, integer over integer, or a terminating or repeating decimal. An irrational number, on the other hand, is just a number that cannot be written as the ratio of two integers, and its decimal form does not terminate and does not repeat. So it's the exact opposite of what a rational number is. So what we do is we check if it's rational, and if it's not, then it's automatically irrational. So a couple examples down below. 2 over 13, this is an integer over an integer, so we can say that this one is rational. Part B, 0.25, this decimal terminates. We don't have to know that this is equal to 1/4, but it is. Okay, and because the decimal terminates, we can say that this is rational, but also by turning it into that fraction, we can see it's rational that way. Part C, 26.8232323. See how those two threes are repeating? We have that dot, dot, dot. That means I can rewrite this with a bar over the 2 and the 3 to represent that the 2 and the 3 just keep repeating over and over. And because we have repetition, this is going to be rational. And then part D, notice we have the dot, dot, dot at the end, 3.14159 dot, dot, dot. Okay, that dot, dot, dot means it does not terminate, and there is no repetition there. I know it might feel like it repeats because you see the number 1 twice, but there's no pattern to that repetition, okay? The 1 shows up twice, but then everything after it is different. And so this one is going to be irrational because it does not meet our definition for being a rational number. It does not terminate and it does not repeat. All right, and then one note, when I say that a repeating decimal is rational and that we can turn it into a fraction, integer over integer, we don't learn how to do that right now because the process requires a little bit more algebra skills. And so that is something that in the future we can definitely talk about and learn how to do, how to turn that into a fraction. But for our current set of abilities, we're not quite there yet. In a couple lessons, we'll have all those skills though. All right, now square roots. You are essentially required to know what all of the perfect squares are up to 15. That way you know how to square root numbers up to 15. Because what a square root is going to do is take us from a perfect square backwards to what we squared to get there. So the actual definition up here, the square root of a number m is denoted with a radical over the m. Okay, so this symbol here, this is called a radical, and it tells us to do the operation square root, where what a square root is going to do is it's going to cancel out a squared on a number. So you can see over here, if m is equal to n squared, then the square root of m is equal to n. So for example, okay, 25 is equal to 5 squared. So the square root of 25 is equal to 5. Okay, where n right here is the 5 and m is the 25. So because 5 squared equals 25, that means the square root of 25 is 5. Okay, so as long as we know several of the perfect squares, and specifically up to 15 is what I'm going to deem as useful, then we can always just go backwards by just knowing what its square was. All right, so we're gonna fill in this table real quick, then I'll come up to that other bullet point. The number on top is 1 in that first column. 1 squared is still just 1. 2 squared is 4, 3 squared is 9, 4 squared is 16. Remember, when I say squared, that means 4 times 4, where there's 2 4s multiplied together. 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, 12 squared is 144, 13 squared is 169, 14 squared is 196. I always remember that one because it's just the reverse of these two digits. So from 13 to 14, I feel is not too hard to remember. And then 15 is 225. And I always remember 15 because if you bench press 2 plates, or if you do any exercise with 2 45-pound plates on each side of a barbell, then it adds up to 225 pounds. So in bodybuilding world, 225 is a very, very popular number. All right, so we need to know all those values. Just like we need to know our times tables, okay, for everything 1 to 10. We need to know all the perfect squares up to 15. It's just going to make life a lot easier. All right, so now that second bullet point up above, okay, looking up here, we can only take the square root of positive numbers. The square root of a negative number will result in an imaginary number, which is what we call any number that is not real. So this lesson is titled Real Numbers. Okay, we don't know what to do with imaginary numbers. So if we have the square root of, let's say, -4, we don't know what this is, okay? This is going to equal an imaginary number, okay? And later in this class, we're going to understand more about imaginary numbers, but for right now, we're just leaving it at that. It's imaginary, we don't know what to do with it. All right, so let's look down. Number 2, if you are able to pause the video and skip ahead and do any of these, I highly recommend you do. But what we're going to do is evaluate each expression, and if that expression is imaginary, then we're just going to say so. And for parts D and E, because they are not perfect squares, we're going to approximate by stating what 2 integers it lies between. Okay, so part A is the easy one. We have square root 36, so all I do is find 36 on my chart right here, and its square root is going to be the number above it, which is 6. Okay, so we can say that square root 36 equals 6, and we can say because 6 squared is equal to 36. We don't need to say that logic every time, but that's really what's happening behind the scenes. Okay, next one, part B. This negative sign is out in front, so I'm going to leave it there. And then square root of 144, if we look at our chart again, 144 is right here. The square root of it is 12, okay, because 12 squared equals 144. So I'm going to say that we have a 12 here, and that negative sign in front, so altogether we have -12. Okay, part C. We have square root of -81. Square root of 81 would be 9, but because there's a negative sign inside of there, we're just going to go ahead and say that this is imaginary. Okay, and we're going to leave it at that. Later in this class, we'll learn that it's 9i, but we don't know that yet. All right, square root 15. What we're going to do is we're going to say where this is between by finding where is 15 in this list of squares. Okay, so 15 is between 9 and 16, which means the square root of 15 is between 3 and 4. Okay, so we're going to say that the square root of 15 would be right in here somewhere between 3 and 4. So we can say that it lies between +3 and +4. Okay, next one, negative square root 40. 40 on this table is between 36 and 49, which the square root of those is therefore going to be between 6 and 7. But because it's negative right here, okay, that negative is going to make it between -6 and -7. Okay, so it's going to be between -6 and -7. And usually, we don't want to write it in this order. Okay, we actually want to write -7 and -6. That way we're writing the numbers from least to greatest. Okay, because -7 is smaller than -6 technically, because it's more negative. All right, switching gears, we are going to now compare fractions. So comparing fractions is clearest when they either have the same numerator or same denominator. It is always an option to just focus on making the denominators the same, which some of you will prefer it that way. But you can also compare fractions by just having the same numerator. Okay, so bullet point 1 says if the numerators are the same, the fraction with the smaller denominator is the larger value. So for example, if we have two fractions that both have 1 on top, 1 over 2 is going to be greater than 1 over 3 because the numerators are the same, but the 3 is a bigger denominator, meaning we're cutting the 1 into more pieces. Okay, so if you cut the same thing into more pieces, each piece is going to be smaller. Bullet point 2, on the other hand, talks about denominators. So if the denominators are the same, let's say they both have a 2 on bottom, okay, then the fraction with a larger numerator is going to be bigger. So if I say 7 over 2, that's going to be greater than 6 over 2, because 7 is bigger than 6, but they're being cut into the same number of pieces. So if I take, let's say I give you $7, and I say to give half to your friend, well, you still have $3.50. If I give you $6 and tell you to give half to your friend, well, now you have $3. So in the original one, I gave you more money to start. I gave you 7 instead of 6. So when you gave half away, you still had a larger amount. Okay, so when you cut it into the same number of pieces, whichever one started with the bigger amount is going to be the bigger overall value. All right, and then the last bullet point, we already know this, but if the numerator and denominator are both the same, then the fractions are just equivalent. So what we're going to do is we're going to convert some fractions here, try to make some things look similar. So for the first fraction, part A here, we're going to rewrite this so that way they have a common denominator. So 4 over 3 and 8 over 6, if I make 4 over 3, if I just multiply top and bottom here by 2, okay, this fraction becomes 8 over 6, and I'm comparing that to the 8 over 6 that was already there, okay, because this one just comes down, and the blue one, I made a new one. So notice now 8 over 6 and 8 over 6, these are just going to be equal to each other. So neither one is bigger, okay, these are equivalent fractions. Because when I find a common denominator, they both have same denominator and same numerator, so they have the same value. Okay, part B though, notice the denominators, 8 and 25, those are not so easy to make the same. So if I want to compare them, I can instead look at the numerators. Okay, it's pretty easy to turn a 7 into a 21. I just have to multiply by 3. So let's go ahead and multiply top and bottom of this first fraction by 3. Okay, that'll give me 21 over 24. And the other fraction, if we just leave it the same, is 21 over 25. So now when we compare, we start with the same amount. They have 21 on top. Okay, so we have 21 in both cases, but in the first case, the blue one, I'm cutting it into 24 pieces, and in the second case, I'm cutting it into 25 pieces. So when I cut it into fewer pieces, that's going to give me a bigger fraction. Okay, so this first one, 21 over 24, has a greater value because their numerators are the same, but I cut it into fewer pieces. Okay, so 21 over 24, I'm going to say, is larger because same numerator, but smaller denominator. All right, for part C, we could, again, focus on the numerators and turn this 7 right here into a 21. But instead, I'm going to find a common denominator. That way we can apply the other rule. Okay, so in here, I'm going to multiply top and bottom by 4. That way I can turn 8 into 32. So this is going to give me 28 over 32. And my other fraction stays the same, 21 over 32. So now we have the same denominator in both cases, but the blue one has a bigger numerator. And so same number of pieces, but if we cut a bigger thing, 28 instead of 21, up into 32 pieces, when you start with 28, each piece is going to be bigger. Okay, so imagine we have a pile of money and we're splitting it into 32 pieces. You would rather have that pile of money be big at the beginning That way each piece is bigger at the end. Okay, so we're going to say that 28 over 32 is larger because same denominator, but larger numerator. Okay, so again, for this one, imagine you're cutting in the two things into the same number of pieces. So if the thing you're cutting up is larger, then each piece at the end will be larger. All right, now a couple applications of this. This is where we're going to learn when we need to round, okay? So it says when solving applications involving real numbers, it often makes logical sense to round our solution. Whether we need to round up or down, though, is going to be based on context. Okay, so it's not necessarily going to be a mathematical reason, it's going to be a contextual reason. Okay, number 4 is going to illustrate this really well. A class field trip will have 110 people attending. If one bus can hold 38 people, how many buses are needed? So what we're going to do is divide here. We're going to do 110. Each bus holds 38. Okay, so 110 divided by 38. 38 does not go into 11. Okay, so if I write out, by the way, whenever you need to divide by numbers that are 2 digits, what I always recommend you do on the side is just write out some multiples of that. So 38 is obviously 38 times 1. And then if I double it, okay, I'm going to get to 76. And then if I do 38 times 3, let's see, we're going to get 90 plus 24 is 114. All right, and notice that 114 is already bigger than 110. Okay, so we can only fit 2 38s into 110. So then I'm going to subtract 76 down below here. Okay, in order to do this subtraction, because 0 minus 6 doesn't work, I'm going to have to borrow one from the next row. So I'm going to take one away from the middle. So then we're doing 10 minus 6 is 4. Okay, then we have 10 minus 3. And so we're going to have 34 here. So what this says is that if we rent 2 buses, okay, so if we use 2 buses, then we will have 34 kids, or 34 people, I should say, because they might not be kids, they might be the adult chaperones. So 34 people left over. Okay, so I could keep going with the division and get 2 point something, but notice that we're talking about how many buses we need to order. So you're not going to order a partial bus, right? We're not going to order 2.8 buses. So instead, we're going to have to round up because of context. Okay, so our answer here is 2 point something. Okay, and I say something because it does not matter, because the context tells us that if 2 buses does not fit everyone, then we need, okay, we need 3 buses. Oh, is there only one S on buses? All right, so I purposely am not finishing the division because it does not matter. Okay, we can keep dividing, but once you don't have enough, like once you have people left over from those first 2 buses, you automatically need a 3rd bus. So whether this is 2.2 or 2.5 or 2.7, it does not matter. We need 3 buses. Okay, so that 3rd bus is absolutely necessary. All right, let's look at a weird scenario here. A rock climbing group for couples is planning an overnight excursion, and they have 14 tents available. If each tent can hold 7 climbers, which is strange considering this is a trip for couples, okay, what is the maximum number of couples the group should allow to ensure everyone can be protected from mosquitoes at night, meaning that everyone has a spot in a tent? Okay, so first we got to figure out how many people can fit in these tents. So the way we do that, we're going to take 14 tents and we're going to multiply by 7 because we can fit 7 climbers in each tent. So 4 times 7, 8, carry the 2. Okay, we can fit 98 total climbers. Okay, well, so we're talking about how many groups of couples, right? How many couples should we allow? So if we do 98 and we divide it by 2, that'll tell us how many couples. Okay, so 2 goes into 9 4 times. Subtract 8 down below, we're left with 18. We get a 49 there. And so in this case, we don't have to round, okay? Because we know that it is exactly 49 couples that can fit in these tents, we can invite all 49, okay? Let's say, though, that we didn't get a perfect number there. Okay, let's say we got 49.5. Okay, if you could invite 49 and a half couples, well, that really means you can still only invite 49, right? Because it's not like you're going to invite half a couple on a couples retreat. That would mean inviting one person instead of a whole couple. And so that would cause us to round down. But in this case, we're lucky. This number comes out clean. Okay, so we can invite 49 couples. All right, now because the title slide question goes along well with this one, I'm going to go ahead and go up to the top. We're going to finish off the title slide. And then after that, in a new video, I'll go over the next part of this lesson. So let's go all the way back up. Don't get a seizure from me scrolling, please. All right, we're back on to title slide 1. All right, so now you're at that resort in Cancun. You have $250 to tip, and you're going to tip $4 each time you get a drink of water. So we want to know how many drinks of water that we can get. So we're going to take the $250 we have. Each time we tip, we are using $4. So we're going to divide by 4. 4 goes into 25 6 times. We subtract the 24 down below. We get 10. 4 goes into 10 twice. So we subtract 8 down below. It's going to leave us with 20. I'm going to have to add a decimal place here to drop down that 0. 4 goes into 20 5 times. And so what this tells us is that we can get 62.5 drinks of water. Okay, but real life context. If you can get 62.5 drinks of water, that actually means you can only get 62. Okay, you're not going up and ordering half a drink in real life. That's just not how it works. Okay, so contextually speaking here, our actual answer is going to be 62 drinks of water. Okay, because again, we need to round this one down because in order to make this make sense in real life, you're not going to go up and order half a drink. You're not going to order 63. We're not going to round up, okay, because then you'd be out of tipping cash or you'd only be tipping half as much on the last one. That's a little rude. So instead, we round down. You can get a maximum of 62 drinks of water. All right, we'll do the rest in the next video. Stay tuned.